Hi, everyone. Thanks for joining. This is joint work with Ariel Prakacha, Alex Psomas, and Asarg Shah. So this work is generally about fairly dividing indivisible goods. So these are things like houses and cars and jewelry. They can't really be split between people. They entirely have to go to a single agent. So our goal is going to look something like this. We're going to take the goods and find some allocation of them to the agents. Just as a quick roadmap for the talk, I'm actually going to spend a bit of time talking about general known fair division things, just as motivation for our specific setting. Then I'll jump into our own results, both the deterministic and randomized. So to be a bit more formal, we're going to have a set of n agents and m indivisible goods. We're going to assume that each agent values each good at some non-negative real number. And we're additionally going to make the assumption that these valuations are additive. So if an agent receives a whole bundle of goods, their value for the bundle will just be the sum of their values for each of the goods in the bundle. Now you might complain this is somewhat of a restriction. It's not a very general setting. So actually later we're going to make an even stronger assumption. So let me at least wait until then to try to justify this. So this assumption is just for now. Our goal will be to find an allocation. An allocation is just a partition of the bundle, of the goods into bundles, one bundle for each agent. And we actually don't require that this partition is complete. So we allow for some goods to remain unallocated. We're also in search of what are known as allocation rules. And these are simply functions. They take as input the agent valuations and then choose a good allocation. So what would we want from an allocation rule? So the classic literature focuses on axioms or properties that we'd hope it would satisfy. And in this work, they're generally going to fall under three categories. This is fairness, efficiency, and truthfulness. Let me dive into a few of the properties that we care about. So in terms of fairness, we'll hopefully choose an allocation that satisfies, well, this is the gold standard of fairness. It's known as envy-freeness. An allocation is envy-free if all agents prefer their own bundle to a bundle received by any other agent. Unfortunately, this might be impossible to achieve, at least in the case when we have to allocate all the items. And to see that, just imagine that there's two agents trying to split a single item that they both like. Whoever gets the item, the other agent will envy them. So in general, we usually instead focus on relaxations of envy-freeness. So one of the most well-known ones is known as envy-freeness up to one good. And here, it's okay if agents envy each other, but they shouldn't envy as long as we remove one of the items from the other agent's bundle. Next is efficiency. And here we focus on the property of Pareto optimality. So we'll hope that our chosen allocation is not strictly worse than any other allocation. What do I mean by that? I mean, there's no alternative allocation, a prime, such that under this other allocation, every agent is at least as well off, and at least one agent is strictly better off. So we hope our chosen allocation A isn't really dominated in this sense. Finally is truthfulness. So here we're hoping to find a good rule such that agents are incentivized to tell us the truth. This makes it easier for the agents. They don't have to think about gaming the system and has other good benefits. So the main one is known as strategy proofness. So no agent can misreport their true valuations and then end up with better utility. And a strengthening of this is known as group strategy proofness. So not only will this be true for a single agent, but there's no group of agents that can misreport such that they all improve their utilities. So on their own, these properties are not particularly difficult to achieve. So I'll show you I can do it here. So let's say our goal is just fairness on its own, specifically EF1. To achieve this, we can do, let's say, round robin. And the way this works is that agents just one at a time take their favorite good of whatever's left. So the blue agent starts by taking the house, then the green agent takes the car, is their favorite goods, and then the orange agent of the ones remaining takes the painting, and blue agent goes again and takes the necklace. If our only goal is efficiency, we can achieve this just using welfare maximization. So just give each good to the agent that values them the most. So in this setting, the green agent values the house, the painting, and the car higher than any other agent, and the orange agent gets values the necklace more than any other agent, so they receive these items. Finally, if our only goal is strategy proofness or truthfulness, one easy way to achieve this is with what's known as dictatorship. So we can just say give all the items to the first agent. This is definitely not fair, but it's truthful. We don't even look at the agent valuation. It's very easy to decide on the allocation. So on their own, it's not too difficult, but let's say we want more than just a single property. Let's say we want multiple properties at once. So for now, let's consider some pairs. So let's say efficiency and truthfulness. To achieve this, we can do what's known as serial dictatorship. So it's very similar to dictatorship, except that if there's any goods that the first agent values exactly at 0, we won't give it to them. We'll instead give it to the second agent unless they value it at 0, and so on. So here, agent 1 actually values the necklace at 0, so they won't receive that. We'll get every other item, but the green agent here will get the necklace instead. How about fairness and efficiency? So this is actually a little trickier. It actually wasn't until even just a few years ago you knew how to do this, and that's what's known as maximum Nash welfare allocations. Let me just take a quick detour and talk about what these are. So at a high level, a maximum Nash welfare allocation is just one that maximizes the product of the utilities, and this is overall possible allocations. Modulus of minor caveats when the product's 0, but that's how it works at a high level. So what was shown just in 2016 is that these allocations are always both fair in the sense of being EF1 and efficient in the sense of being PO in the general additive case. Although unfortunately, it's also known that they're not truthful, so they don't satisfy any strategy proofness properties. And what about any other combinations? Unfortunately, these are actually known to be completely impossible. So you actually can't get fairness and truthfulness in combination for these general additive valuations. This was shown about 3 years ago. And even if we just wanted efficiency and truthfulness, the only option was the one I showed you, serial dictatorship, which is definitely not fair in the slightest. It's not even close to being all three. And actually, this is even true if agents are not just restricted to report any non-negative real number, but just 3 distinct valuations. So what can we do instead? Well, one possible solution that we consider in this paper is binary valuations. So we're going to make the extra restriction that not only are valuations additive, but agents can actually only report either 0 or 1 for each good. So why binary valuations? First of all, although they're definitely much less expressive than other forms of valuations, they're incredibly easy to elicit. So it's pretty well known that humans have a hard time of placing specific values on things. Binary valuations are particularly easy to elicit. We just, for each good, we ask the agent, do you like or not like this good? So it's very simple. I will say that in general, additive valuations also pose somewhat of a trade-off. They somewhat represent quite a good sweet spot in the middle of both being relatively expressive, but also relatively easy to elicit. We can just ask for each agent what their value for that good is, rather than asking for like every possible subset of goods, which could be quite difficult and quite taxing on the agents. In some sense, these binary valuations represent an extreme point on this expressiveness elicitation Pareto frontier. Binary valuations are quite similar to another very well-studied concept, and that's approval voting in voting theory. So here, when agents vote on things, they just say whether or not they approve that alternative, which is, in a very similar sense, a binary choice. These are very well studied and are actually used quite often in practice in several real-world scenarios, and these binary valuations are just the equivalent in the fair division setting. Finally, binary valuations have been relatively well studied in the literature, And they are of theoretical interest, mainly because we can think about maybe what extra properties they can satisfy here. With extra restrictions gives us more power. And this leads to a next obvious question, which is, can binary valuations help us achieve our goal of getting all three of these categories, properties in these categories, simultaneously? And in this work, we answer this affirmatively. So we introduce a new rule. This rule we call M&W tie. So it chooses an arbitrary maximum Nash welfare allocation such that two things hold. First of all, we're not going to allocate non-valued goods. So these are goods that every agent says they value at 0. We're not going to give those to any agent. They're going to remain unallocated. Finally, if there are multiple maximum Nash welfare allocations that give different values to different agents, we're going to tie break first with respect to agent 1, so maximize their utility among maximum Nash welfare allocations, and then given that, maximize the utility agent 2, and so on. So just to give you an example, if these are the valuations, note that they're all binary, this would not be an acceptable allocation chosen by M&W tie, and that's because the phone here is valued by 0 by everybody, and therefore it should not be allocated. Similar here, we're tie breaking in favor of agent 2. Agent 2 is getting 2 utility when it's actually possible to find a max Nash welfare allocation where agent 1 gets 2 instead of 1, and the other 2 agents get 1. So a good example is something like this, but there might be multiple. So this is another option, and M&W tie can choose one arbitrarily. So this rule satisfies several nice properties. So first of all, since these are maximum Nash welfare allocations, and this is strictly more restrictive setting, it's still fair and efficient. So this is stuff that's already known from the past. But in this work, we prove it's actually a very strong form of truthfulness. It satisfies group strategy proofness. On top of this, the rule is also polynomial time computable. Although it was known in the past how to compute an arbitrary maximum Nash welfare allocation, we show how to extend this to our rule, which is not actually totally obvious, mainly because there may be an exponential number of maximum Nash welfare allocations, and our rule is only allowed to choose a small subset of them. So that's all well and good. It's pretty much as good as we can get for these types of properties. But what if we want even more fairness? So recall, as I said before, if we want to allocate at least all the valued goods, there's no way we'll be able to get full envy freeness with deterministic allocations. So just to remind you why that is, imagine this scenario where we're trying to split this one painting over 3 agents. There's not really much we can do. Like ideally, we could treat this good as divisible. If we give it to entirely to a single agent, other agents will envy them. But if we could divide it up, then that would make all the agents happy. So do something along the lines of this. And my idea is that we can actually simulate this using randomization. But with randomization comes some interesting subtleties. So when you're thinking about randomized allocation rules, there's a difference between properties that are satisfied as ex-ante, which means they're satisfied in expectation, and those satisfied ex post, which means they're satisfied in every allocation of support. So it means it's importantly, it's satisfied in any actual realization of the random chance. So to show you why this is important, ex-ante envy freeness is actually really easy to achieve, and the way to do that is with random dictatorship. So you just randomly pick a person at random, and then just give all the items to them. So this is in expectation envy free, because in expectation, every agent is getting the same possible set of goods. But is this really fair? I mean, in any actual instance, one person's going to walk away with all the items, and every other agent's going to be somewhat envious of that agent. We really do need to consider ex post guarantees. Of course, if this process is repeated many times, then it's possible that the randomness will even out, and over time, agents will be relatively okay with the allocation. But in situations like these kind of allocations, they often only happen once or a few times, and then it's really important that the ex post guarantees are satisfied as well. Ex ante just isn't enough. So we look at a different randomized rule. This is actually just fractional maximum Nash welfare. So here we're maximizing the product of expected utilities over all possible probability distributions over allocations. So it's actually a very well-studied rule. It's very common in the divisible setting, goes quite far back in the economics literature. It's known that the expectations of these rules satisfy very good ex-ante properties. So in particular, they're fair in the sense of being envy-free. They're efficient in the sense of being fractionally paradoxical, which is even stronger than paradoxical. In addition to that, they're truthful in a very strong sense, in the sense that they're ex-ante group strategy proof. But what we show is that not only are these ex-ante properties satisfied, we can decompose these expectations and find an actual probability distribution over deterministic allocations, such that every allocation in the support is itself a maximum Nash welfare allocation. In expectation, it will be a fractional maximum Nash welfare allocation, but each of these deterministic allocations is also maximum Nash welfare. And because of that, it's both fair in the sense of being EF1 and efficient in the sense of being paradoxical. So these are our main results, and that's pretty much what I wanted to talk about. But since I have a bit of time left, I'll talk a little bit about some of the ideas in the proof, which is not super important to the results themselves, but just to give you some intuition about what it looks like to work with these binary valuations. So a really key tool that we use in pretty much all of our proofs is the envy graph in allocation. So this is just a directed graph with agents as nodes. And there's going to be an edge from I to j if I likes one of the goods in j's bundle. What I mean by like, I just mean that they value one of the goods at 1 rather than valuing it at 0. A really useful operation is known as passing back along a path. So if there's a path in this envy graph, we can pass back along it. What I mean by passing back is that you take the last agent and take a good from their bundle and give it to one of the previous agents that agent actually likes. Since there's an edge, we know such a good exists. And we can do this for every agent along this path. A very useful lemma was proved in 2018 by Barman et al. And at a high level, it says that any Pareto optimal allocation A is a maximum Nash welfare allocation if and only if there is no path in the allocation such that the agent at the end of the path has strictly more value than one more than the starting agent. So Vj of Aj is strictly more than Vi of Ai plus 1. So this is a really nice equivalence between this envy graph and maximum Nash welfare allocations. Some other really important ideas that we use, if we consider LT to be the set of agents with utility at most t, and ST to be the set of agents reachable from LT in the graph, so we'll say this includes LT themselves, we'll allow 0 length paths, we actually get some really nice properties. So in particular, if we have a maximum Nash welfare allocation, we get this very nice nesting of these sets. So L0 is contained in S0, which is contained in L1, contained in S1. The L contained in S is pretty trivial because that's just the definition of being reachable. We'll definitely include it. But the S's ST being contained in ST plus 1 is a very nice property of maximum Nash welfare allocations, and it follows directly from this lemma. But it's very useful in many of the proofs when you want to talk about agents reachable in the graph. In addition, these sets ST must collectively receive all the items that agents in the set like. So what I mean by that is that if there's a good that any one of the agents in ST values at 1, then that good must be allocated to one of the agents in ST. And this is very useful in proving things like strategy proofness or other structure in the allocation. So I'll wrap up here. So I'm going to say that these maximum Nash welfare allocation rules are just about as good as you can get with binary valuations, where we're very happy with the properties they satisfy. Of course, there's still room for a little bit of improvement. So specifically in the deterministic setting, we require that our allocation rule didn't allocate all the items. It left the non-valued goods unallocated. So an open question here is there a deterministic rule that allocates all the goods and also achieves all the properties we wanted? So EF1, PO, and GSP. Unfortunately, if a rule only allocates maximum Nash welfare allocations, it's impossible for it to do it. There's no way it will satisfy group strategy proofness, so it must sometimes choose non-max Nash welfare allocations if it were to be able to do this. In the randomized setting, there's a little bit of improvement possible in the truthfulness requirement. So our rule satisfies ex-ante strategy proofness, but is it possible to improve this to ex-post strategy proofness? So I mean by that is that the rule, it'll be ex-post GSP if it's actually a probability distribution over deterministic GSP rules themselves. But nonetheless, our rules are still very strong and satisfy many of the positive properties that we like of these allocation rules. Anyways, that's all. Thank you for your time.